we can start our first session on waste-to-energy technologies. So the objective here is to discuss the advancements on these technologies. So there is ongoing project with the National Institute of Technology, Tiruchirapalli, and the Tomsky University, and of course the Federal University of Rio de Janeiro. That's why we invited Professor Anand Ramanathan, Associate Professor from the National Institute of Technology, Tiruchirapalli, and then Professor Dmitry Kushlov and Professor Pavel Strikhek from the Tomsky Polytechnic University. Professor Anand Ramanathan is an associate professor in the Department of Mechanical Engineering at the National Institute of Technology, Tiruchirapalli. His area of specialization involves internal combustion engines, and it spans to the field of alternative fuels, waste-to-energy conversion, emission control, and fuel cells. As a recognition of his contributions, he was awarded with the Inyanga Memorial Prize in 2009, Outstanding Scientist Vira Award in 2017, and Dr. Krishnan Award in 2018, and the Best Performer Factual Award in the National Institute of Technology, Tiruchirapalli, in 2020. I mean, this year. Professor Dmitry Gushkov holds a PhD in physical and mathematical science, and he is an assistant professor of the National Research Tomsky Polytechnic University. Expert in combustion theory, and his area of research is combustion processes and composite solid propellants and gel fuels, co-combustion of solid fossil fuels, and municipal solid waste, micro-explosion of composite fuels, hotspot ignition. Dr. Glushkov has 66 publications in the last 5 years in Scopus and Web of Science. Professor Pavel Strikhek also holds a PhD in physical and mathematical science, and he is professor of the National Research Tomsky Polytechnic University. Expert in heat and mass transfer theory with phase transition and chemical reactions. His area of research is combustion processes of liquids and composite fuels, reduction of anthropogenic emissions, micro-explosion, multi-component liquid fuels, and forest fires. Professor Strikhek has 263 publications the last 5 years in Scopus and Web of Science. So again, thank you very much, Professor Anand, Dmitry, and Pavel, for accepting, delivering a presentation for us. So we start with Professor Anand. So Professor, the floor is yours, or the screen is yours.
So good morning, good afternoon, good evening, everyone. I thank Professor Amro Ferreira for a nice introduction. And also, I welcome the panelists, Dimriti and Pavel. I think I can start my presentation. Yeah. So the topic of my presentation: waste to energy conversion technique by pyrolysis process. As you know that lot of waste is generated. The world generates 2 billion tons of municipal solid waste annually, with at least 33% of that extremely conservatively not managed in environmentally safe manner. Worldwide, waste generated per person per day averages 0.75 kilogram per, I can say, but ranges widely from 0.11 to 4.5 kilograms. Though they
Sorry,
only
Anand.
yeah.
Just to make sure, are you in the first slide or in the second?
I am in the first slide. Yeah.
Okay, sorry, thank you. Yeah, just to make sure that it is working.
Okay. Yeah. So know that I can say around about they only account for 16% of the world population. High income country generate about 34% of the solid waste of I can say 83 million tons of the worldwide waste generated. India produces 277 million tons of municipal solid waste every year, according to 2020 estimate. Brazil produces 62 million tons of solid waste per year. As you know that as you know, it has the potential of converting this waste into a useful product in form of either in form of solid, liquid, and gaseous products. It has some kind of energy content, and finding out the suitable application will generally, I can say, will minimize the waste which will be generated across the globe. As you know that biomass considered to be one of the best potential source available in across the world. India produces about 450 to 500 million tons of biomass per year. I mean to say that biomass per year is a waste biomass coming out from I can say different agricultural residues and forestry. Biomass provides 32% of all primary energy usage in country at present. Ministry of Renewable Energy Sources estimate MNRE India estimate that potential for power from biomass in India is about 18,000 megawatt as per the reference cited. The current share of biofuels in total fuel consumption is extremely low and is confined mainly to 5% blending in ethanol gasoline. Now we all know that ethanol manufacturer Brazil is a I can say top manufacturers of ethanol from the different I can say different bagasse or different I can sweet potatoes and other related source. Even I can say Brazil they are using a gasoline engine with the maximum blending of I can say blending with petrol. So Brazil is the leading this one usage of the biofuel in case of internal combustion engines. Ministry of Renewable Energy has been implementing biomass power for co-generation for both power as well as the heat generation. A total of 280 biomass power and co-generation projects is available in of a capacity of 2,665 megawatt is installed in the India, which can combined with a maximum 158 bagasse co-generation projects in sugar mills with surplus capacity aggregating from 1,666 megawatts. So, well, you're supposed to know what is biomass. Biomass considered to be one of the potential source, all organic matter generated through photosynthesis and other biological process. It consists of bio plus mass. Bio means is a biologically derived substance which has some kind of mass. That is why it's called biomass. Different biomass you come across in daily, I can say, experience. You may come across wood and forest residues, waste from food crops. Then different waste comes out from the kitchen, then from the food processing industries, animal waste, manure, and I can say which is rich in phosphorus. Then human waste, which has the potential of energy, which can be converted into either a fertilizer or in the form of liquid or gaseous fuels, which can be fed into the different applications. Yeah. So we know that there are different compositions which are available in the biomass. Lignocellulose biomass utilization has gained the worldwide attention due to the property of green, copious distribution, and renewable source. The residues from agricultural activities and forest environments are the important source of lignocellulosic biomass. Major chemical constituents of the biomass is hemicellulose, cellulose, and lignin in terms of 39%, 31%, 18% by weight respectively. Okay, this photograph reviews talks about the different biomass sources available. You can see here in the rightmost one, you can see here the cellulose content is major in terms of biomass, 39%. Hemicellulose will be available. If you take any biomass either in the forestry waste or agricultural residues, you can find out from the chemical composition of different biomass. Cellulose, hemicellulose, and lignin is a major constituent present in the biomass. So, and then you can find out the application. You want to convert the biomass into a liquid fuel or gaseous fuel or the solid fuel. So, accordingly, it's going to be differs. So, what is the significance of the biomass? What are the significance of energy which is going to get derived from the biomass? It is a renewable source of energy. So, you can. It is not going to. It's not going to be exhaustible. You can get at any point of time. And also I can say the cost of I can say feed material you are going to use it for biofuel production or bio energy generation will be very low when compared to fossil fuels of coal and then oil as well as gaseous fuels. Biomass is consume more CO2. That is very much advantageous. Whereas we can say by consuming the fossil fuels, it liberates a lot of CO2, which is increasing the global warming, can say, constituents. Global temperature increases because of the increase in the CO2 level. Whereas if you make, I can say, biomass as a source, and if you cultivate it very far lands or dry lands, you can able to, I can say, grow the trees or other kind of agricultural products. It is going to consume the whatever may be the CO2 available in the nature. So the energy balance, CO2 balance is going to be happened by using the biomass. And also you can see here there are a lot of biomass. Not I can say still it's not going to be utilized in terms of application point of view. We are not going to use the biomass from the edible source. We are still lot of few millions of I can say species are available now. Not I can say traced out so far for utilization of converting into energy. It can, and also by increasing the biomass utilization or growing the I can say biomass resources, it can stabilize the soils. That is very much important, and improve the soil fertility and reduce the erosion. There are different biomass conversion technologies are available. It may be familiar to you. I can say starts from pyrolysis, gasification, and combustion. So you may be familiar with all the places from Asia or Europe or many places or in the olden eras, right? Where the combustion you may be familiar with this. You can burn the fuel in the presence of oxygen or in the presence of air with providing the ignition source. But what is the problem with combustion is it produces a lot of emissions. Apart from the liberating energy, it also produces a lot of particulate matters and soot. This is going to, I can say, deposit on the humans as well as animals pods, I can say pods, and it will damage and also it will increase the photochemical smoke across the during the, I can say, for many places like in Delhi and other places. So the safer way of utilization of biomass, growing attention. The best way to use is going for gasification and pyrolysis. Gasification is a method in which you can burn the fuel in the, I can say, not with respect to the chemically corrected air fuel ratio. You are going to use a 20 to 30% of the air requirement. You can burn the fuel, I can say incomplete combustion happens, but not, instead of producing the carbon dioxide, you are producing carbon monoxide. And the product comes out from the gasification is the rich in carbon monoxide and hydrogen. We call it as the producer gas or syngas. Then the syngas, we can use it in a Fischer-Tropsch process to convert into liquid fuel. Whereas in terms of pyrolysis, the product comes out from the pyrolysis process, the liquid one. So if you feed either a high density liquid or the solid fuel, by using a different methods of slow pyrolysis or fast pyrolysis, you are going to get three products. And it depends upon the operating temperature and residence time in which you are going to operate the pyrolysis process, you are going to get the three products, biochar, bio oil, and gas. So if you want more, I can say liquid, you can increase the temperature of the reaction. There are three methods generally we are utilizing for converting the solid biomass into either if you want a liquid or a gas or to burn the fuel, I can say, by using the combustion method. So pyrolysis is the method we are currently working in NIT Tiruchi, and we are with respect to I can say Tomsk Polytechnic University and COPE, Brazil. Professor Amro also contributing for the two projects. One is from Spark, another from the BRICS project. So we are likely to work on the pyrolysis. Pyrolysis is the thermal decomposition of the material you are going to feed it into pyrolyzer at I can say at elevated temperature. But you are not adding any kind of oxygen or air into the system. In the absence of, I can say, air, you are doing the process. Ultimately, you are going to get three products: solid material, liquid, and gaseous products. So this liquid, you can use it in an internal combustion engine or a thermal power plants or gas turbine power plant. Whereas the char, we can use it as a catalyst, to convert it into a catalyst, or you can use it as a fertilizer. Whereas in the gaseous fuel, you can either use it in an internal combustion engine or a gas turbine, or you can use it in the like a steam power plant or gas turbine power plant. The products comes out from the pyrolysis is in the form of hydrogen, methane, and carbon monoxide, and I can say, and the oil. So you want to operate the system in the absence of air, that is the inert in nature. So mechanism of pyrolysis, I can say, you can do the process breaking down the, I can say, pyrolysis is nothing but lysis and pyro. Pyro means heat, lysis means break down the higher molecules, heavier molecules, the small molecules. So the product you are going to get from the pyrolysis in the form of liquid, gas, as well as the solid. But whereas in case of pyrolysis, you are going to get the maximum amount of liquid apart from the solid and gaseous products. So there are many biomass sources are available, and we have done with the component called we can say in our campus we have used the Classia fistula, the golden shower tree. You may be coming across. That is a waste material is now is going to pollute the environment, and it's going to, I can say, the waste is going to be generated in a huge amount. So we are taking it as a converting take it out the seed and the shell, and we convert it into a solid product which can be grinded into a fine size. Then we can take it to the pyrolyzer. We can use it either thermal pyrolyzer or electrical pyrolyzer, or recently we are using a microwave pyrolysis. As you know that microwave is energy intensive, also energy intensive process, but the amount of energy consumed for, I can say, melting the solid biomass is going to be comparatively lower than the electrical as well as the thermal pyrolysis. And also the heat is coming from inside to out. That means the losses of energy from the surrounding is going to be minimized. We go for microwave pyrolysis system. And the product you are going to get a condensable as well as the non-condensable gases. Condensable gases, you connect it to a condenser, convert it into liquid, we call it as a bio oil. Non-condensable gases, you can take it for some kind of thermal application, you flare it, or you take it to the engine for burning the non-condensable gas to convert into power. Whereas the solid residue is going to be generated in the pyrolyzer, or either it's a microwave or thermal or electrical pyrolyzer, you can convert into a fertilizer, or you convert into catalyst form of converting it to activated carbon. Seed you can directly convert it into liquid. Okay, so this is the photographic view of I can say oil are extracted from the pyrolysis process, particularly microwave pyrolysis. Then the non-condensable gases, no, it is not going to be condensed. Then you can burn it. We can use it for any kind of heating application, or in terms of burn it, take it in the internal combustion engine. You can use it in a diesel engine. You can burn it and you can produce the power, or you can have a standby diesel generator. You can use it for producing the power. Yeah, before you do for the any kind of biomass sources, it is our duty to ensure that you do for scanning under microscope study to ensure that what may be the morphology of the particular species you are going to take. So before doing the process, we have taken the morphology. After that, we have taken this B is nothing but a biochar. Biochar has the potential. We can use it for activated carbon. You can come across in purifying the wastewater. So the biochar, whatever you are going to generate from the pyrolyzer, is going to be utilized as a source material for purifying the water. So we are going to get three product. Solid, you can use it for many applications, wastewater treatment as well as for converting into catalyst. Then we can use it for fertilizer. Liquid, we can use it for internal combustion engine and gas turbine application. Gaseous one, you can use it for internal combustion engine, or you can take it for gas turbine as well thermal power plant. So nothing is going to be wasted. So and also the whatever way the gas comes out, you can burn it efficiently without polluting the environment. So pyrolysis properties, if you say that, you can take it for gas chromatography spectroscopic analysis. You can find out what are the different species of hydrocarbon present. Then you can find out from that what may be the energy content you can able to find. You can compare with the petrol and diesel. As you know that petroleum products, is coming around 48,000 kilojoules per kg. Diesel is comes around 45,000 kilojoules per kg. The bio oil is not at all going to be inferior to the petroleum products of gasoline and as well as the diesel. It is comparatively equivalent to that of diesel because bio oil is a non-volatile fuel, so we can directly use it in a complete replacement of the diesel fuel. It has a good property. So if you take out the property, you can say that for bio oil, gasoline and diesel and biodiesel and vegetable oil, you can see here the density of the bio oil will be slightly higher than that, but especially I can see here viscosity and all are slightly higher. Flash and fire point is it is much higher, much higher than this diesel and petrol. That means there is no problem of transporting this fuel. And also this fuel you can see here, it is very near to, then you can operate at the place where the temperature and the fluid liquid likely to be frozen. That means we can go up to minus, I can say 20 degrees centigrade. The place where the temperature not falls below minus 10 degree, you can use it conveniently. Otherwise, you can use some kind of additives in this pyrolysis oil. Then you can use it efficiently. Okay, so you can see here it is approximately 60% of the calorific value of the diesel. That means you can say only thing you're going to increase the volume of the diesel tank by twice. And you can see here the density and the thing is comparatively higher. So you have the methods to reduce the viscosity as well as the density, that you can blend it with some kind of diesel or other kind of the liquid fuel which has the lower viscous as well as the lower density in nature. So after this, you can find out, if you want to find out for particular biomass sources, what may be the operating temperature of the biomass, that you can find out from using the thermogrammetric analysis and the digital scanning calorimetry, how much the heat is needed for completely convert the solid to liquid. That you can find out. You can see here from here, the maximum loss in mass is going to be happened at, I can say, at a temperature of 600 degrees centigrade, 550 to 600 degrees centigrade. That means that you can operate this biomass at a temperature of 550 to 600 degrees centigrade. So you can completely convert into liquid. So you can see here from this one, you can able to by operating the temperature at different thing. You can see here there are different biomass yield bio oil yield you are getting, bio oil, biochar, and non-condensable. If you increase operate at 550 degrees centigrade, the solid content will be product will be more than the, I can say, non-condensable gas and bio oil. If you operate above that 500 degrees or 600 degrees centigrade, the bio oil constituent will be more than the bio and non-condensable gas. So the temperature plays a major role in pyrolysis process. When you go for slow pyrolysis or medium pyrolysis or fast pyrolysis, and the residence time in which you are going to operate it, that decides the product yield, whether you want liquid more or solid more or gaseous products more. That depends upon the operating temperature. So there are different constituents you are going to get from these gas chromatography. You can see here hydrogen, carbon monoxide, methane, carbon dioxide, ethylene, and ethane, and all you are getting. And you can see here hydrogen is a good products coming out by using some kind of method. You can separate out hydrogen. We can be used for either in the form of, I can say, fuel cell applications. Yeah. So various process. I think I'm going to take maximum 5 minutes. Then the pyrolysis oil has once you produce the oil from the biomass, we are going to get 3 phases: A and B and C and D phases. You can see here 15%. A phase that should be have higher I can say lower density. B and C is the intermediate density. D is the higher density. Okay. So you can see here the A phase is nothing but water and acids and organic acids for fertilizer. We can use it for fertilizer. B phase is cellulosic acids. Normally the phenols are phenols suitable for fuels and chemicals. So there are three different layers are you are getting. You can separate out according to the separate different density. Then it has several applications. Okay, A you can use it for fertilizer. B phase you can use it for chemicals and fuels. C phase you can use it for fuel and chemical feedstock preparation. Then D phase you can use it for binder or char granules for pellets. So non-condensable gas, there are several products: hydrogen, CO2, CO, and other things are there. It also has a potential application. You can use it for gas turbine or internal combustion engine or thermal power plant. Okay, you have to flare it up. It has also the energy content. So you should not leave it to the surrounding. It has some kind of hazardous constituents are available. Biochar, after converting the biomass into I can say bio oil or non-condensable gases, whatever may the residue is going to be left over in the pyrolysis called biochar. We call it charcoal. It is carbon rich in nature. It has a potential application of converting into I can say minerals or to contain inorganic minerals from biomass. You can use it as a fertilizer, or you can use it as a convert into catalyst for any kind of Fischer-Tropsch reaction or other any kind of reaction. You can act as a catalyst, or you can use it as a activated carbon, converted active carbon. You can use it as a wastewater treatment. Yeah. So different feedstocks are available. You can see here rice hulls, wheat straw, softwood, and each one is operating with a different temperature, because from the TGA study you can find out what way the operating temperature for different feedstocks. So it depends upon the temperature the product is going to be arrived. So importance of biochar I already explained. I don't want to retain this one because it has the whatever maybe the biomass we are taking out, it has to again go back to the earth as a fertilizer. It has a potential application to, I can say, for used as a fertilizer for growing the trees and other agricultural crops. So different applications, bio oil. So you can convert this as the chemical. You can use it for I can say chemical products. You can use it for fermentation, convert into ethanol. We can use it in a petrol engine. Then you can use it in a turbine or diesel engine fuel. And you can use it as I can say fuel for power plant, thermal power plant, particularly for steam turbine power plants. Then you can use it for converting it to some kind of refinery method. You can use it to take out the hydrogen from the syngas, which will be generated from the either the pyrolyzer or gasifier. You can use it for fuel cell applications.
And just to let you know, you have 2 more minutes.
Yeah, I likely to be there. Coming to the conclusion.
Okay.
Okay, so there are different pyrolysis processes are there. So the different that varies from slow based on the operating temperature, intermediate pyrolysis, and then residence time. So we are classifying the pyrolysis into 3 types. So most preferable one is flash pyrolysis, operating at temperature of 450 to 900 degrees centigrade. The residence time within, I can say, every heating rate is 2 degrees per second. So the microwave pyrolysis is going to be a recent research they are doing it, because it has a lot of potential. Whatever the energy is needed for converting into liquid will be minimum for converting the, I can say, liquid to the maximum level. So because the energy generated inside goes from the inside system to the surrounding, so the losses will be minimized. Okay, so there are table shows the different pyrolysis process with respect to operating temperature. Depends upon the product you need, either solid, liquid, or gas. This is going to be differs. So different properties I already discussed. So conclusions: biomass pyrolysis has been attracting the much attention due to its high efficiency and good environmental performance characteristics. It also provides an opportunity for the processing of agricultural residues, wood waste, and municipal solid waste into clean energy production. In addition, biochar sequestration could make a big difference in the fossil fuel emissions worldwide and act as a major player in the global carbon market with its robust, clean, and simple production technology. So these are the references I have used for preparing this presentation. I would like to thank my scholars Dinesh and Dinesh Junior as well as Dinesh Senior for helping me to prepare the slide for this presentation. Thank you one and all for patient listening, and thank you Amro. If you have any questions, and you can free to interact with me.
Thank you very much, Anand. It's too much information, so we have to be in our time. So, by the way, send my regards to Vinitz and and Dinesh Junior and Senior. Thank you very much.
Thank you so much.
We can move to the Dimitri's presentation. Dimitri, the screen is yours now.
Good morning, dear colleagues. Professor Amaro, thank you for introduction. My name is Dmitry Glushkov. I'm Associate Professor of Tomsk Polytechnic University, Russia. I would like to present you our experimental research results that we obtained during the last half year when carrying out an international scientific project in collaboration with the scientific teams of Professor Amaro Pereira and Professor Anand Ramanathan. The subject of this project is life cycle assessment of carbon dioxide reduction by energy efficient hybrid biomass pyrolysis and gasification. It should be mentioned that this topic is new for our scientific team because the main fields of research are combustion process of various fuels and propellants. By the way, we have obtained new experimental results in biomass pyrolysis and gasification that we use for development of mathematical models. In our presentation, I will discuss only experimental results connected with non-condensable products of pyrolysis. Okay, at the beginning, I would like to tell several words about motivation of present study. Biomass is the fourth largest energy source after coal, oil, and natural gas. It is a renewable source and a carbon-neutral fuel with an additional advantage of low nitrogen and sulfur content. Therefore, biomass is currently one of the most promising renewable energy sources. Using biomass in thermal power engineering can make a difference for the economic development and rural regions. Improve the internal energy security of a country due to the variety of availability biomass resources and low level of greenhouse gases as opposite to fossil fuels. The main methods used to process biomass for power generation, the thermochemical and biochemical. The last one methods such as extraction and hydrolysis are more expensive and sophisticated in their practical implementation. Combustion, gasification, and pyrolysis is the most widely used thermochemical ways of biomass conversion. Each method has advantage and disadvantage. Gasification and pyrolysis represents interest in this study because new products can be produced during this process, such as liquid or solid fuels and a group of materials for chemistry. As you can see on the scheme of biomass pyrolysis is a multi-level physical and chemical process converting an organic fuels into a gas at temperatures between 600 to 1500 degrees Celsius. A gasifying medium can be air, oxygen, water vapor, carbon dioxide, or a mixture of them. The generated syngas consists of methane, carbon dioxide, hydrogen, carbon monoxide, a small amount of light hydrocarbons, and other pollutants. The concentration of each component of the gas mixture mainly depends on the process conditions in a reactor, local conditions in fuel sample, and chemical composition of biomass and the structure of gasifiers. Apart from syngas, the typical biomass gasification products are biochar, biofuel, and heat. The biggest challenge of gasification is the production of tar. It significantly reduces the quantity of syngas and interacts with the reactor walls. In contrast to gasification, pyrolysis proceeds at high temperatures in inert gas atmosphere. Pyrolysis can be used on its own or can be main stage of chemical reactions during gasification and combustion. In conclusion of the first part of our presentation, it should be mentioned that biomass is a high potential alternative energy source and feedstock to produce useful products for the chemical industry. The purpose of our study is experimental research of pyrolysis characteristics for a group of various biomass and their mixture with varying process parameters in a wide range. Experimental setup and procedures will be presented in the next part of the presentation. Appearance of experimental setup shown on the slide. The main part of setup is the pyrolysis furnace, position number 1. Contains electrical heaters and thermocouples. Temperature was varied from 300 to 700 degrees Celsius. In experiments, the furnace were preheated to a necessary temperature. Fuel samples, position number 5, with weight several grams, was entered to furnace through viewing window, position number 12. During short time period, it should be mentioned the temperature decrease in furnace no more than 30 degrees Celsius. The main part of experiment was conducted at the air atmosphere with initial oxygen concentration about 20 volume percent. Besides, we did experiments in CO2 and water vapors environment. The process occurring during biomass heating were registered by 2 gas analyzers. They are test 340 position number 8 and test 1 position number 10. The first one is a standard industrial configuration. It measures concentration of five gases. Test 1 is an analyzer with customer design according to our requirements that were produced by Russian manufacturing company Bonaire. The main characteristic of this analyzer is presented in table 1. There was no access of outside air to the furnace during the experiments. The duration of the experiments was about 30 minutes. The gases left after the experiments were removed from the chamber by blowing air through it. We conducted no less than 3 runs at the identical initial conditions. The next table is illustrate kinds and characteristics of biomass widely used in fuel technologies all over the world. Based on this data, we choose only 3 typical kinds of biomass for our experiment study. They are sawdust, straw, and leaves. We conducted experiments with those individual components and their blends. The main obtained results will be presented with accordance of the investigated parameters and effects. They are component properties and concentration, biomass moisture, thermal condition, ratio of pyrolysis products with CO2 and water vapors on the combustion chamber, mass, shape, and surface structure of samples, dispersion of components, a mixture of biomass with other components. Experiments for leaf, straw, sawdust in the 3 blends were conducted at the identical initial conditions. Compositions of blends you can see on the 3 right columns. It was obtained that the pyrolysis of blends is more efficient. Depending on the ratio of components in the biomass mixture, it is possible to increase the CO emissions by 2.542%, methane by 30%, and hydrogen by 22%, and to reduce the carbon dioxide concentration by 25% and nitrogen oxides by 77%. According to obtained results, the biomass blends number 3, sawdust 25%, straw 50%, and leaf 25% is more perspective for following investigations. The next investigative factor is the biomass moisture influence on the compositions of gas mixture. At the bottom of the slide, you can see typical trends of carbon dioxide, hydrogen, and methane concentration during the pyrolysis. Average values of gas mixture components during this process are presented at the top of the slide. The higher the biomass blend moisture, the higher the concentration of useful gases. In the next step, we establish influence of temperature in the furnace on the concentration of gas mixture components. The higher the temperature, the more intensive physical chemical process occurred during the pyrolysis. As you can see in table 4, higher temperature leads to decreasing of solid residue. But concentration of harmful gases grow up more rapidly in comparison with concentration of useful products. Therefore, the optimization problem must be solved to determine the effective temperature of biomass pyrolysis. It will be realized with using of mathematical model of process in future. Next two slides illustrates influence of air change in the combustion chamber to water stream and carbon dioxide on the pyrolysis characteristics. Table 5 illustrates influence of water vapors on the gases concentration. The higher the water steam concentration, the lower the concentration of carbon dioxide and methane, and the higher the concentration of nitrogen oxide and hydrogen. Next results illustrate that we obtain significant increase in concentration of carbon monoxide and carbon dioxide, methane and hydrogen during pyrolysis when the oxidizing environment in the chamber were replaced with flue gases. Of course, experimental samples were influenced significantly on the integral characteristics of the process, such as volume of produced gas mixture, but concentration of its components did not vary significantly. In our experiments, we found that the shape of experimental sample and the structure of the surface affect the characteristics of the process in conditions of the equivalent initial weight of biomass blend sample. We explained that the obtained results by the difference in the degree of biomass conversion with different methods of preparing experimental samples. It should be mentioned that the size, that the biomass particle size, about 240 micrometers, is more efficient in comparison with other two values. In the first case, when the particle size was 2 millimeters, the degree of biomass conversion is not very high. In the second case, when the particle size was about 120 micrometers, the above mentioned parameters is high enough, but the cost of the grinding biomass is too high. Next two slides illustrates influence of various additives on biomass blends on the pyrolysis characteristic. We used various kinds of coal and municipal solid waste. It has been established that this direction is promising for further experimental study. At the end of my presentation, I would like to present the main results. The typical products of thermal decomposition of biomass are carbon monoxide and carbon dioxide, hydrogen, methane, nitrogen oxide, and hydrogen sulfur. The variation rate of gas concentration presented on the slide. Like in case of combustion, the pyrolysis of mixture has proven to be more efficient. It was established that depending on the rate of components in the mixture, one can increase it is the useful components of flue gases, while another one can be decreased. It is the harmful components due to synergetic effects from the interaction of various biomass components and the pyrolysis products. Thank you for attention. If you have any questions, I would be pleased to answer them.
Thank you very much, Dmitry. So it's time for questions. So if you have any, you can write in the chat. You can see in your screen. So I have one question for both of you, Dimitri and Anand. First is I saw that the calorific value in in Anand's presentation is very high, but can you both compare the calorific value of the oil, pyrolysis oil, and the syngas?
Yeah, in terms of energy content of syngas, usually in terms of in the volume. So normally in case of a liquid fuel, comes in the form of pound. So if you see that the energy content of syngas, when you compared with liquid fuel, particularly gasoline or diesel or pyrolysis oil, is not going to be comparable. So always the calorific value of the gaseous fuel will be lower than the calorific value of liquid fuel. So there's no comparison of gaseous fuel with, I can say, liquid fuel. Only thing, the diffusivity of the gaseous fuel is likely to be much faster than the diffusivity of the liquid fuel. That I can say. In terms of storage perspective, liquid fuel will be better than the gaseous fuel, because in order to produce the same amount of same volume of energy content by using a pyrolysis and diesel or petrol, you can carry within, I can say, small tank. Whereas if I want to produce the same energy content, if you want to travel, if you want to move your vehicle from the one point from the stationary to some distance, amount of energy needed for, I can say, in terms of energy density, will be comparatively higher in case of liquid fuel than the gaseous fuel. So gaseous fuel, in terms of emissions perspective, I can say you will get a lowest emissions, but in terms of storage of fuel, it has drawback. Energy, in terms of energy perspective also, energy density perspective also, it has a drawback. But the only thing, as the conventional fuels keep on depleting, so you have to depend upon this some kind of alternate fuels. So either in the form of liquid or gaseous fuel. So in that case, without having anything, and we can have something, so that way you can run the vehicle. Thank you.
And Dimitri, can you compare? You produce syngas as well, or only pyrolysis oil? Can you compare
Syngas,
the syngas with the LPG, for example, in terms
now
of calorific value?
normally for a thermochemical conversion technologies, we want, whether you are interested in getting a liquid fuel or gaseous fuel. If you want more gaseous fuel, again particularly the concept of carbon monoxide hydrogen, we call the syngas. Right? You want to convert 1 kg of biomass solid residue to, I can say, completely to, I can say, gaseous product, maximum of gaseous fuel. Then you can go for gasifier, not a pyrolyzer. When you want to convert the solid residue into a liquid fuel maximum, you can go for pyrolysis process. Right? What is the advantage in going for I can say pyrolysis process is you can convert it solid to liquid. That means the transportation of the fuel in terms of energy density will be very high. Suppose we are taking care of the municipal solid waste or medical hazardous waste. There, if you convert into gaseous product, then it will, I can say, it will produce a lot of emission because it has a lot of pathogenic in nature. So in that case, pyrolysis is going to be a better method than best method than the gasifier. Suppose we're talking with agriculture residue, I can say you can want hydrogen product going to be higher, then you can go for gasifier. Then you separate out hydrogen from the carbon monoxide from the syngas, then we can use it as hydrogen for fuel cell application. Whereas if we want to run it in a gas turbine or a thermal power plant, or I can say in terms of internal combustion engine, the best fuel is going to be a liquid fuel. Then in that case, you will go for pyrolysis. When there is no issue of storage, then you can go for gasification. Go for produce the gaseous fuel, no problem at all. But But when you want to carry the fuel, the best fuel is a liquid fuel. So in that case, pyrolysis is going to be a best method for producing liquid fuel. Professor Amaro, I think I answered your question. I think
Yes, you did. You did.
yeah, I'll add to this. Professor Dimriti can.
Yeah. Would you like to add something, Dimitri?
Oh, it's excellent comments of Professor Anand. I agree with him, but I would like to say that the main purpose of our study was to obtain main parameters of pyrolysis characteristics, and that we would like to use in our mathematical model. We don't have the purpose to measure calorific value of pyrolysis gas, but it should be mentioned that in our study we obtain only pyrolysis gas, not syngas. Syngas is a gas with special characteristics and components. And I can say that according to our results, calorific value of pyrolysis gas significantly depends from the feedstocks and from the parameters of pyrolysis, and it can vary in big variations. For example, from 20 megajoule to kilogram to 40 megajoule to kilogram. Yes. Okay. Thank you.
So I add to this, Professor Dimriti. Syngas has only two compositions. One is carbon monoxide and hydrogen. Whereas the pyrolysis gas, we have carbon monoxide, carbon dioxide, methane, then ethylene and ethane. So there are many constituents are present in the pyrolysis gas. The pyrolysis gas, we are having two constituents. One is called condensable gas and this non-condensable gas. Condensable gas, we are taking it to the condenser to convert into liquid, whereas some of the gases are not going to be condensable with respect to the coolant. So that we call it as non-condensable gases, that you can use it for either for running the internal combustion engine or gas turbine, or you can take it for thermal power plant for producing the power. So, that's all. Thank you.
Thank you, Anand and Dimitri. There is another question here. I'm going to read. The major challenges I experienced when dealing with renewable fuels is the combustion properties of these fuels. Can you comment how can you increase the methane and cetane index? These are critical parameters when trying to use these fuels for power generation.
Yeah, there are some there are some additives are available, particularly for improving the cetane index and cetane improvers. That as Brazil is producing a lot of ethanol, right? And also the from the conventional fuel, coal or something, right? We are producing the methane, right? So the hydrolysis of the methane and I can say the ethanol, we are oxygenated methanol and ethanol. We call it as a dimethyl ether and diethyl ether. Similarly, for higher alcohol starts from methanol, ethanol, propanol, butanol. If you convert the methanol and ethanol into ether based, methanol is CH3OH, ethanol is C2H5OH. Whereas if you convert into CH3O, CH3, that is dimethyl ether, then C2H5 C2H5, we got as a diethyl ether. These are all very, very good, I can say, ethanol based additives, which has very, very high cetane index of more than 125, greater than 125, particularly for diethyl ether, the derivative derived from the ethanol, which is coming from the renewable fuel of ethanol, from the bagasse or other corn or sweet potato, right? So the cetane index improvers are available, you can see commercially, or you can convert the methanol ethanol into ester based, I can say alcohols from the alcohols. And it has a very good, you can blend it with in terms of few proportions. I can say in terms of petrol or the diesel or in the pyrolysis oil. Pyrolysis oil, if you measure the cetane index value, it comes to around nearer to, I can say 50 to 60. But it's comparable with the diesel. Diesel cetane index, cetane number is coming around 45 to 50. In terms of cetane index comes to 50 to 60. Whereas in order to improve further, I can say if you think that your pyrolysis oil having cetane index value is less than 45 as per the ASTM standard D6751, American Social Testing Material suggested by cetane number is 45. If you feel that your pyrolysis oil having low cetane number of less than 45, the only way to improve the cetane number is add some additives in the form of oxygenators, a dimethyl ether and diethyl ether, because we have 2.5 times more than the petroleum products, and it will be, I can say, 3 times higher than the pyrolysis oil. By adding in terms of 5%, 10%, or 15%, you can able to measure the, I can say, cetane number by using some kind of testing methodology, or by finding out the cetane index by using the distillation process. For every 10%, 50%, 90% evaporation, what will be the temperature you are going to get? Then you can substitute this equation, you will get the cetane index. So the best way to improve the cetane index is use some activated additive which is derived from the alcohols, methanol and ethanol, even for higher alcohols. That's all from my side.
Thank you. Would you like to
Okay.
add something, Dimitri?
Okay, I have several ideas in our presentation and in our experimental results. We obtained that the concentration of methane can be increased by moisture increasing of initial biomass, and besides, as said Professor Anand, we can use co-pyrolysis, for example, of biomass and coal, and so we can reduce significantly the concentration of methane in pyrolysis gas. Thank you.
Thank you. Also, I saw in the Dimitri's presentation that he has some experiments with mixing biomass and coal, for example. And Anand, you are studying to mix biomass and plastic. How is the outcome of the pyrolysis oil with this mixture in both cases?
Yeah, the plastic is a derivative of the petroleum product. There is very good hydrocarbon content is there. Whereas biomass contains a maximum of, I guess, lignocellulosic materials, which has high ash content. Whereas plastics doesn't have any ash content. Even if you burn it, you will get only few traces of ash. Whereas if you burn the biomass, you will get, I guess, at least 20 to 30%. No, I can say 10 to 20% you will get ash products because of solid residue. And petrol, if you use the plastic, I can say directly in the open, I can say in the combustion mode, it produces carcinogenic emissions. So if you blended the plastics in terms of 90, I can say 5% plastic, 95% biomass, then 90% biomass, 10% plastics. As they know that the plastic energy content will be much higher than the, I can say, slightly higher than the energy content of the biomass. So by adding the blending of plastics in the biomass, the energy content is increasing from, I can say, 25, I can say, megajoules from kg to even you can go for 30 to 35 megajoules per kg. And also you are not only you are increasing the energy content, also you are reducing the plastic which will be available in the, I can say, as a waste which is available in the across the globe. And also you are using the pyrolysis system which is not going to be contact with the atmosphere. It's going to be there as an inert atmosphere. Whatever maybe the gas will be generated, it will be converted into a liquid. The form of condensable get converted liquid. Non-condensable gases, we are going to burn it in the internal combustion engine. That means nothing going to be released to the surrounding, the form of incomplete products. That's why I can say by making use of the plastics and in terms of blending with either in the form of convert the plastic into of powder, you blend it with a biomass powder, you can increase the energy content, can increase the calorific value of the fuel, and also you can able to reduce the plastic. Plastic is going to be a biggest problem, I can say, is going to be generated across many places, even the marine as well as the land pollution. So if you are able to consume the plastics for converting into energy, and also by using a pyrolysis, you can able to convert the plastic into a useful form of a chemical, then you can able to reduce the, I can say, plastic generation across the globe. Yeah.
Okay,
Dimitri,
I have several ideas. Well, unfortunately, we did not conduct experiments with the pyrolysis of plastic in this year, but we plan these experiments in the future. But I can say that previously we conduct experiments with co-combustion of low-grade coal and plastics and different types of municipal solid waste. One of the main problem it is the harmful gases that produced during the combustion process, or for example during the pyrolysis of these components. The main harmful components is dioxins and furans, and it should be use special technological operation for decreasing these components. For example, it is high temperature of the process of pyrolysis of combustion. Its temperature should be about from 1000 to 1200 degrees Celsius. And the next step it is quick recurring of flue gases. These two operations can decrease concentration of dioxins and furans for convenient values. That's all. Thank you.
And I added to this one, and when you burn the plastics, during the combustion, plastics are made up of with hydrocarbon material along with some kind of additives made up of chromium and bromine. It's a very toxic materials. So if you operate this plastic at an elevated temperature of more than 1500 degrees centigrade, the bromine and chromium will tend to form some kind of carbon oxides formation. So normally in the pyrolysis, we are operating at a temperature of 500 to 700 degrees centigrade. So there is no issue of, I can say, the product comes out from the form of bromine or chromium oxides. So that we can able to eliminate, and also we are operating in an inert atmosphere. Then there's no, and also you can say try to reduce the formation of these toxic emissions. It will be formed during the additives will be mixed for converting into a plastic, some kind of product, which can be eliminated in the pyrolysis process. Thank you.
I think we have time for one more question. I saw in your presentation, Adam, that you get 20% of, more or less 20% of water content. After drying the biomass, you have still 20% of water content.
Yeah, you cannot eliminate the moisture content less than probably I can say 8%. So even then, by going for any kind of highly sophisticated drying methodologies, so moisture cannot be eliminated. And also the lignocellulose material having hydrogen nature. So when it finds some kind of reaction with this moisture, so it tends to break the water. It will tend to form the water vapor. So aqueous formation is going to be a big, I can say it's a big problem in pyrolysis process, because it will reduce the separation process also. So we are struggling a lot for eliminating the water which is formed in the pyrolysis process. Dinesh Junior is really facing some problem separating. That's why we are gone for every, I can say, 5% drop in moisture content will increase the pyrolysis pyrolysis yield by 10%. We have found that. So increase in the value. If you drop the moisture content by 5%, then you can able to get the pyrolysis yield from 30% or to, I can say, from 20% or 30% to, I can say, more than 10%. We are still working on it, and the biggest problem in handling the biomass in the pyrolysis process is the aqueous formation. So we have to really, because the water will totally spoil the, I can say, the oil formation. So this is not going to be eliminated, because we cannot eliminate the moisture content less than 10%. So that will be going to be there. Even after the, I can say, heat is produced, the water will be evaporated. Because as the density of water is around 1000 kg per meter cube. So it will be going to be there in the top of the layer. So you can heat it above 100 degree. I can say you can able to remove the water from at atmospheric pressure. But some of the water, I can say, it's miscible with some I can say the acid component which is there in the bio oil. So elimination of water, because as you know, the bio oil is hygroscopic in nature. It tends to absorb the moisture from the surrounding. As already we are providing the moisture, I can see available in the biomass itself. So during the reaction, the moisture will, I can say, will be the moisture will be absorbed. The water vapor will be absorbed by the bio oil. It will increase the density of the bio oil. So there are methods are available to reduce the water content which is available in the bio oil. But as it has a hygroscopic, you have to store it very carefully. Even if you open it to that produce a bioshell, keep it in the atmosphere, then atmospheric, I can say, air will, as a moisture in nature, which will be absorbed by the bio oil. So density will be keep on increasing if you are not properly sealed the bio oil. Thank you,
Thank you very much,